Hello and welcome to this session, Learning Outcome LO3. Understand the structure of matter today. We will learn what makes materials behave the way they do under stress. Understanding the structure of matter is crucial in physics and engineering. This video explores crystalline, amorphous, and polymeric structures and how they influence material properties. Crystalline materials have atoms arranged in a regular, repeating pattern. This ordered structure gives them well-defined physical properties. Metals, for example, have atoms in layers that can slide under force. This makes them both strong and malleable. Understanding this helps in applications like metal forming. Amorphous materials lack a long-range ordered atomic structure. Their atoms are arranged randomly, unlike crystalline materials. Examples include glass and many ceramics. These materials tend to be brittle, breaking suddenly when stressed. This randomness impacts their physical properties significantly. Polymers consist of long-chain molecules that can be tangled, aligned, or cross-linked. Their properties depend on chain length and bonding between chains. Polymers often show large elastic deformation. They also exhibit time-dependent behavior. This makes them versatile for various applications. Metals consist of positive ions in a lattice with delocalized electrons. This structure allows metals to conduct electricity and heat efficiently. They can deform plastically without breaking, making them ductile. Their unique properties are utilized in numerous industrial applications. Understanding this is key in material science. Bone is a composite material made of collagen fibers reinforced with mineral crystals. This combination gives bone both strength and flexibility. It can absorb energy without fracturing easily. This makes it a fascinating subject in biomechanics. Studying bone helps in developing better prosthetics. Elastic deformation is temporary and reversible. Materials return to their original shape when the force is removed. Metals like copper show elastic behavior at low stress. This obeys Hooke's law within limits. Understanding this helps in designing springs and elastic systems. Plastic deformation is permanent and occurs after the elastic limit is exceeded. Common in ductile metals, this behavior is crucial in metalworking. Brittle materials like glass show little plastic deformation. They fail suddenly once the elastic limit is exceeded. This understanding aids in material selection for engineering. For many elastic systems, force is proportional to extension. This relationship applies to springs and elastic wires. The gradient of a force extension graph represents stiffness. This concept is vital in designing mechanical systems. It helps predict how materials will behave under load. Understanding terms like ductile, brittle, and elastic is essential. Ductile materials can be drawn into wires. Brittle materials fail with little deformation. Elastic deformation is proportional to force. These definitions are crucial for interpreting material behavior. Dislocations are defects in the crystal lattice that allow atoms to slip. Plastic deformation mainly occurs through dislocation movement. Metals are strengthened by hindering dislocation motion. Techniques include alloying and work hardening. This increases strength but may reduce ductility. In brittle materials, failure occurs by crack propagation. Stress concentrates at the crack tip, causing rapid growth. Reducing surface flaws increases breaking stress. Techniques include using thin fibers or compressing surfaces. This understanding is crucial for preventing material failure. The work done deforming a solid equals the area under the force extension graph. If Hooke's law applies, this is the elastic potential energy. This concept helps in energy storage applications. It is crucial for understanding material behavior under stress. Engineers use this to design resilient systems. Stress-strain graphs provide insights into material behavior. They show regions of proportionality, elasticity, and plasticity. Identifying the elastic limit and breaking point is crucial. These graphs summarize how materials respond to load. Engineers use them for material selection and design. Tensile stress occurs when a force stretches a material. Compressive stress occurs when a force compresses it. The formula for both is force divided by area. Materials like concrete are strong in compression. Understanding these stresses is key in structural engineering. Strength describes a material's ability to withstand stress. Breaking stress is the maximum stress before fracture. Brittle materials reach breaking stress with little deformation. Ductile materials deform plastically before breaking. This knowledge aids in choosing materials for different applications. Correct. Stiffness measures resistance to deformation. Young's modulus quantifies stiffness in the elastic region. A high modulus means the material is stiff. A low modulus indicates flexibility. These properties are essential in material selection for various applications. Dislocations allow metals to deform without breaking. They move through the lattice under stress. This movement is key to ductility in metals like copper. Restricting dislocation movement increases strength. Understanding this helps in developing stronger materials. Crack propagation causes failure in brittle materials. Stress concentrates at crack tips, causing rapid growth. Reducing surface imperfections can increase breaking stress. Techniques like toughening glass help prevent failure. This knowledge is vital for designing durable materials. Elastic distortion occurs before plastic deformation. Young's modulus describes elastic distortion for a given stress. It indicates how stiff or flexible a material is. This helps in predicting material behavior under load. Engineers use this to ensure safety and performance. Elastic distortion occurs before dislocations move or cracks propagate. Dislocation movement leads to plastic deformation. Crack propagation leads to sudden failure in brittle materials. Together, these concepts explain material responses to forces. Understanding them is key in material science. In conclusion, understanding the structure of matter is crucial for predicting material behavior. From crystalline to amorphous forms, each structure influences material properties, making this knowledge essential for engineering and materials science applications. For further questions, please contact us on WhatsApp at 07484361688. Thank you for listening. We'll see you at the next session.